Hi everyone, welcome back. We're actually here. I cannot believe we're already at exam 2. So this video is just going to cover the bulk of material in chapter 16. This is not all of chapter 16 though. There will be another video after this finishing up those extra topics that are like tautomerization and alpha halogenation, etc. So that will be in a separate video. This is kind of the meat and potatoes of oxygen-based nucleophiles and nitrogen-based nucleophiles adding into carbonyls. So without further ado, let's just jump in. So kind of just giving you some reference on where we are. So chapter 16 is all about adding in different various nucleophiles, such as carbon-based nucleophiles, nitrogen-based nucleophiles, and oxygen-based nucleophiles, all into these carbonyl groups, either aldehydes or ketones. And in the last exam material, we talked about the Grignard reaction, which was adding in a Grignard reagent into an aldehyde or ketone. We talked about an organolithium addition, which is adding in an organolithium reagent into an aldehyde or ketone. And finally, we talked about acetylide addition, where we took that alkyne anion and added that into a carbonyl aldehyde or ketone as well. Remember, Gilman reagents do not react with aldehydes and ketones, and that's pretty much all we covered for chapter 16 material for the last exam. So the new exam 2 material picks up on the last carbon-based nucleophile addition, which is the Vidiq reaction. So there are 4 total. We did 3 on the last exam, and this is the new one that we didn't get to cover. Just some things to keep in mind. They could come up again, so I would go back and watch that video. It is all encompassing, so definitely take a look at that. So this is the Vidiq reaction. So first of all, we have this molecular species called an ylide, and all an ylide is it's a carbon-phosphorus bond, and that carbon is a negative charge and that phosphorus is a positive charge. So an ylide is really just something like this, and there could be things attached to these atoms, but just like an abbreviated version, that's what an ylide is. It's just a carbon-phosphorus bond with varying charges on top of them. So how do we prepare ylides? So let me zoom in over here. So we have some sort of alkyl halide, and we have these series of steps. So the first step is something called triphenylphosphine, and the second step looks like some sort of base. It's a source of hydride. So let me just move over here so you can see what a triphenylphosphine looks like. So it's literally just 3 benzene rings attached to this phosphorus, and we have this lone pair over here, and we realize and we can rationalize that that lone pair is going to be used in nucleophilic attack somehow, okay? So let's just look how we're going to prepare an ylide, back over here. So recall that triphenylphosphine, like I just showed you, actually has a lone pair on them, and that is a source of electrons. Even though it's not negatively charged, it is a source of electrons. And remember, if we rationalize with haloalkanes, that we have a dipole moment in the direction of the electronegative atom. In this case, it's chlorine. So that makes that this carbon at this position an electrophile, and we already established that triphenylphosphine is the nucleophile in this case. So if I were to draw the mechanistic arrows, it would look something like this. And this is very similar to what type of reaction back in Organic 1. If you said SN2, that is totally right. This is governed by SN2 factor, so sterics. So just to keep in mind, if you wanted to prepare an ylide, you're kind of limited into this type of alkyl halides that you can use. Only primary and certain secondaries would be acceptable. All right, so the product of step 1 would be something like this. So this is that new carbon-phosphorus bond that we built over here, and we have a positive charge on phosphorus. So step 2 is actually an acid-base reaction, and sodium hydride is just one of the bases we can use. You could have used butyl lithium, which is an organolithium reagent, or you could have used sodium amine over there. So those are very good bases that you could use, but in this case we're just going to use sodium hydride. So if I were to just draw on these hydrogens that are adjacent to that phosphorus, we can rationalize that we're going to have a source of hydride, and the mechanistic arrows are as follows. Okay, so the product of this would be and that's my ylide. So now we've prepared this ylide, and we can use this ylide in a Vidiq reaction to extend the carbon chain, replace a carbonyl with an alkene, okay? So just to make another note here, sometimes we don't always see the ylide in these, I guess, Zwitter ion state. A Zwitter ion is just a term for a molecular species with a positive and a negative charge in it. So another time, sometimes we do see a resonance version of this, which is where these lone pairs are just resonated in to kind of fix those formal charges. So this is also equivalent. Okay, so either one is acceptable. You're probably going to see this version more because, you know, we're minimizing that octet, so it's a more favorable structure, contributes more to the overall resonance hybrid. But in terms of reactivity, this structure is actually more useful to see the reactivity, but this one over here is more stable. All right, so that is preparation of an ylid. It's just a series of nucleophilic attack by SN2 reaction and then an acid-base step to perform that ylid. Pretty easy. All right, so let's talk about some stereochem. I know it's everyone's favorite, but there is some to consider in this reaction. So we have these ylids in this situation. We have two specific ones we want to compare here. So if I were to just resonate those pi electrons out to see the reactive conformation of this structure, we would see something like this. I'm just going to redraw that over here. And I'll redraw this one over here. Okay, so these are my two ylids. So the question I want to ask myself is, are these ylids stabilized in any sort of way? Is there resonance? Is there induction? Is there anything like that that is further stabilizing or delocalizing that negative charge over the entire atom? So if we look at this structure over here, we see that we have these lone pairs, and we want to see if we can push them out in sort of resonance or anything like that. Well, we totally can do that. We can take these lone pairs, push them in. We can take these lone pairs we can take this pi bond, either make it a lone pair or swivel it over. It's extensively stabilized via resonance. You can see that pretty dramatically. Over on the right side, we see that we can't really participate in resonance. Even if I were to try and move those lone pairs in, we exceed the octet rule, so that doesn't happen. So we classify the ylid on the left as stabilized, and we classify the ylid on the right as unstabilized. So what does that mean in terms of stereospecificity and the Vidiq reaction? Well, stabilized ylids are always going to produce E-alkenes, while unstabilized ylids are always going to prefer to form Z-alkenes. And although we don't really discuss the mechanistic points of why, I can just tell you right now it has something to do with the transition state and how the sterics are involved with a trans arrangement versus a cis arrangement, but we do not require you to know that. Just realize that if we have a stabilized ylid, we have E-alkenes, and if we have an unstabilized ylid, we're going to form a Z-alkene. All right? So those are the stereochemistry considerations. So now let's just do an example, and we'll talk about the key mechanistic points. All right? So we have this aldehyde, and we have this ylid over here, and is this ylid stabilized or unstabilized? Well, if you said stabilized, it's correct. If you resonated those electrons out, these pi electrons out, we actually have an ylid that looks like this. Okay, and you can see that through extensive resonance, it can resonate into this carbonyl group and resonate that up, so it is stabilized, so we're going to predict it's going to form an E-alkene. Okay, so let's just do the mechanism for this reaction so that you guys get a better idea of what's happening here. So I'm just going to redraw these starting materials over here. Okay, so recall that we discussed at the beginning of chapter 16 the carbonyl group is electrophilic at that carbon because of two different rationales. One was the electronegativity of that oxygen atom is pulling electron density towards the oxygen and away from that carbon. In addition, we also saw the resonance rationale where if we were to resonate those pi electrons in the carbonyl up onto the oxygen, we would get a full formal positive charge on that carbon as well. So we can know that's an electrophile, and we already rationalized that the carbon on the ylid is a nucleophile. So we would expect that these, let me just erase these so it's more clear, that these electrons would actually attack into that carbonyl and push that up. So the product of step 1 is going to be something like this. Oops. let me just count my carbons to make sure I'm not wrong here. 1, 2, oxygen, 1, 2, oxygen. Perfect. All right, so the next mechanistic step is going to be kind of obvious. We see that we have a negative alkoxide anion over here, and we see it's adjacent to this partial positive phosphorus. So it would make sense that since opposite charges attract, that we have mechanistic arrows from this lone pair to that phosphorus to form a ring. So the product of that step would be something like this. Okay, so that is the product of that mechanistic step. And now here we're going to talk about the equilibrium and the thermodynamic favoring of this reaction. So the only reason why that the Vidiq reaction happens is because we form a very, very stable byproduct. And the byproduct is this structure. So before I say anything further, I want you to try and rationalize why that would be favorable. Well, that oxygen-phosphorus double bond is extremely, extremely stable. It's a strong bond, so the formation of that is what actually drives the completion of this reaction. So basically, we can rationalize that these electrons from this carbon-oxygen single bond are going to want to participate in the formation of this oxygen phosphorus double bond, but at the same time you exceed the octet at that phosphorus position, so these must collapse and come down. All right, so those are the kind of cyclic arrows that we see, and we'll have a whole chapter on pericyclic reactions later on in Orgo 2. But the end product of this is going to be something that looks like this. Alrighty, so if we were to look at the end products, we want to always make sure that we formed either the E or the Z alkene. So let's just look at these end products for a second. And if I were to put my plane of symmetry through that single bond, the double bond, I can label my priority group. So I have a 1 over here, a 2 over here, a 1 over here, and a 2 over here. So if I were to classify that, that is most definitely E. So we definitely have the right alkene at the end. So that is the product of this reaction. So if we were to just do a predict the product situation, we saw in the original carbonyl, we're going to replace that oxygen atom with the entire group that is this over here. So that's a 1,2 carbon chain with that associated kind of ester functional group. So let's just verify that in the end product. We do have a 1, let me change colors here so you can see the carbon count. We do have a 1,2 carbon chain with the associated ester. So we do know that we are correct. I would definitely recommend that you should check your end products to make sure that you have the right structure. All right, so that is the end of the carbon-based nucleophile addition reactions. So now we're just going to talk about the oxygen-based nucleophile additions. So let's just jump right in. So the first one is called hydration of carbonyls, and hydration is just a fancy term for adding in water. And I have yikes in parentheses because this reaction is not favorable at all. All right, so if you see something like this, that's pretty much your trick question on this exam to know that this reaction is not favorable. So let's just kind of look at our experimental percentages over here. So if I were to add in water under the catalytic conditions of acid, we see that we form like pretty much almost 100% of the original starting material and about 1% of the hydrated version of this molecule. So why is that? Well, I can just look at this molecule and rationalize that we have two very bulky hydroxyl groups in a ring next to each other, so that's a significant strain. So I can say strain or sterics over here. And when you look over here at the carbonyl one, that carbon-oxygen double bond, we talk about that all the time, that it's very strong and very favorable, and it's not sterically hindered. So it would make logical sense that we have this reaction. In addition, we saw that there's really no additional stabilizing features in terms of pushing the equilibrium to this product, so we really just don't have a reaction here. So if you saw something like this on an exam, we would definitely say that there is no reaction happening here. But I do want to just point out something with formaldehyde. So formaldehyde is that one exception, and it does make sense. So if I were to do this reaction, again under acidic conditions, we will see that we form exclusively almost 100% of this gem diol over here. And that makes sense because even though that these two hydroxyl groups are bulky, we only have two single hydrogen atoms that are also bonded to it, so we can freely rotate, so maybe something equivalent to this would make more sense. maybe something like that, how they can freely rotate around and move around in space. So, you know, these structures are more favorable, there's less steric hindrance, so the only exception to the hydration of carbonyl groups would be if you had a formaldehyde type example. This is the only type that you would see. All right, so that's pretty much it. That's it. That's easy. So let's move on to the alcohol addition, which is a lot of details. So let's just look at this schematic that I have over here. All right, so we have a couple of different functional groups that we have not talked about before until this point, and they're called hemiacetals, hemiketols, or acetals and ketols. So they sound confusing, but they're really not that bad, and let's just take the first example with the aldehyde. So obviously A and A would make sense that they go together, so the acetals and the hemiacetals are derived from the aldehyde, where the ketols and the hemiketols are derived from the ketone. So if we were to look after adding one equivalent of methanol under acidic conditions, we would get a product that looks like this. Okay, so this is a hemiacetal. So a hemiacetal is a functional group where there is a hydroxyl group, an ether group, a hydrogen, and a generic R group attached. That is what a hemiacetal functional group is. So just like you guys know that a carboxylic acid is a carbonyl with an OH attached to it, this is just what a hemiacetal is. There's nothing more to it. It's just an OH, an ether group, an H, and a generic R group attached to each other. Okay, so that's adding one equivalent of methanol in. So now if I were to continue this reaction and keep pushing through, adding another equivalent, I would expect a product that looks like this. Oops. Okay, so clearly we're replacing that final OH group with another ether group. So the definition of an acetyl functional group would be two ether groups, a hydrogen, and a generic R group. Okay, so that's what an acetal is. All right, so let's just do it with a ketone. So if I zoom in over here, again, I'm adding in an equivalent of methanol. So after one equivalent, we would have a structure like this. And then adding a second equivalent would form the ketol. So now you would expect two ether groups and two R groups. Okay, so the difference between the hemiacetals and the hemiketols is the absence of a hydrogen group. So over here you can see that we have, I'll just call this R and R prime, and over here we have R and R prime. Over here we had a hydrogen and just a generic R. Over here we had a hydrogen and just a generic R. So these are just functional groups. You just got to know them. They're not really too difficult. To me, it logically makes sense, but that is what we're doing in the alcohol addition reaction. So now let me talk a little bit more about the detail about these reactions. So equilibrium considerations. So just as we saw above with the hydration of these carbonyl groups, they are not, these reactions are just not favorable. The formation of a carbon-oxygen double bond, we saw that with keto-enol tautomerization, we saw it with the hydration that we saw above. These carbon-oxygen carbonyl groups are very stable in the way that they are, so they don't like to form these acetal or ketol products. The way that we can drive the equilibrium to form these acetal or ketol products is described by Le Chatelier's principle. All right, so let's just take this picture from your textbook. I really like it. This is what I was talking about when I wanted to show you what a Deanstark trap is. So we have this, if we look over here, we have this aldehyde or ketone, and we're adding in alcohol, and we are forming acetal and water. So think back to Gen Chem, your Gen Chem knowledge. I know it's a long time ago. But Le Chatelier says that if I add a stress to a system, the equilibrium is going to shift to alleviate that stress that was added. So, for instance, if I add excess alcohol, so over here, if I add excess alcohol, that means that I'm going to counteract that stress somehow by forming more products. So that makes sense that if I have an excess amount of alcohol in my solution, in my flask, then I'm going to form a lot more acetal instead of that carbonyl group. Likewise, the inverse of Le Chatelier's principle says if I remove water, if I remove a stress from the system, equilibrium is going to shift to alleviate that stress. So if I'm removing the water from the right side, the equilibrium is going to still shift to the right side to fix that issue. So that means if I take water out, the equilibrium is also going to form more acetal. So this device is actually really cool. I kind of think about it as a cloud. So this flask over here is my reaction vessel. We don't really need to know all the details going on, but let's just say it has my carbonyl phenyl group, so it's either an aldehyde or a ketone. It has some acid in it, and it has my alcohol in it, excess alcohol. So this reaction is happening, it's occurring, and we're forming these volatile vapors that are kind of traveling up, all up in here and whatever. The coolest thing is, and I don't think you guys get to do this anymore in an organic lab, I got to do it with the reflux condensers, but what happens is that hot vapor, you know, like hot air rises in the environment. What happens is that we're going to actually have this current of cold air floating in this sleeve. So it's literally like a sleeve that surrounds this tube, and it's cold air, very, very cold, chilled air, and it causes condensation. So it's just like how clouds form. You have hot water vapor rising from the ground, and then when it gets to a high enough altitude where it's cold, we're going to have condensation. So now these water droplets are going to precipitate back down, okay? And with this stopcock over here, I can open it, and water's going to drain out. So that's equivalent of me removing water from this reaction. This apparatus is actually really neat, and it's Le Chatelier's principle in real life. So just thought it'd be cool to show you guys how we remove water from these, I guess, acetal or ketol reactions. So definitely really interesting. So I have seen on previous exams where it has you explain the equilibrium and how I can form and drive the acetal ketol product. So there are two considerations, and I just said it. Definitely have excess alcohol, so I'll just write excess ROH, and definitely I would have the removal of water, and that can be with the Deanstark Trap like we saw over there. So definitely kind of cool things that we see going on. So now it makes sense that we have removal of water, removal of water, removal of water. Okay? So let's move on and do specific examples of these. So here we have ethanol, that's what ET stands for, with an acid catalyst and the removal of water. So let's just talk a little bit about this for a second. It could be base catalyzed. We do see acid catalyzed more often. It makes more sense logically in terms of reactivity, but base does still work. But for this worksheet, and I'm pretty sure for this exam, you're just going to see acid catalyzed. And I just want to make a note. If you did not see the removal of water, you need to think about the equilibrium for a second. If I did not see a removal of water, this reaction would not happen. Because remember, we need to force that equilibrium to completion to the acetal product, and without using a Deanstark trap, we can't do that. So keep in mind the little details. This exam, it's definitely going to come into play, I think, with trick questions. So just keep your eye on that. So ethanol looks like this, you know, and we have that associated proton in solution. So we're expecting that we have this reagent of protonated alcohol. And remember, we have these lone pair electrons on that oxygen that can add into that oxygen. Actually, I'm sorry, I skipped a step. The purpose of the acid in solution is to actually grab a proton, okay, and activate the carbonyl. So let me just talk about that after I draw this product. So you guys are going to see for the rest of the semester that the role of acid with carbonyl-containing compounds is to make the electrophile more electrophilic. So electrophile, more electrophilic. And that's going to make more sense in about 5 minutes when I talk about nitrogen-based nucleophiles. But just keep your eye on this for now, that the purpose of the acid in solution is to take a proton from the protonated reagent. So in this case, it's this ethanol reagent, and it's going to make that electrophile more electrophilic. If I did not have acid catalyst present over here, the ethanol couldn't just add into the carbonyl by itself. It just doesn't happen. You have to make the electrophile more electrophilic in order for a weak nucleophile to attack. So I know that may have been a whole bunch of different words, but let me just make it a little bit more simpler. If I had a strong nucleophile and a weak electrophile, that would work. But if I have a weak nucleophile and a weak electrophile, that doesn't work. So weak and weak doesn't work, but strong and weak would work. So the role of the acid is to make it a strong electrophile instead of a weak electrophile, and now add in this weak nucleophile as well. All right. So if that didn't make sense, rewind it. Listen to me say that a couple times again. You should really understand that chemical logic. All right, so now I have a fully protonated carbonyl, so now it's a good electrophile. So I can now add in this equivalent of ethanol directly into my carbonyl. Oops. Okay, so the product of that schematic would be something like this. Okay, so we have this product, and the next series of steps are just going to be acid-base transfers. And we are going to show two different ways to show this. So the first way is the long way, which is what you're not going to do in the exam. And we can just take a molecule of ethanol, And what we can do is we can take off a proton from here, and we can form a fully protonated alcohol again. So it's something like this. I apologize, guys. And here we go. So now that we have that fully protonated, alcohol again, the role is to make this group a good leaving group. So remember, hydroxide is not a good leaving group, but water is. So by taking off a proton from the alcohol that I added and transferring it to that hydroxyl group, I actually get a good leaving group. So something along the lines of this. Okay, so you have these series of lone pair electrons on that oxygen that can resonate down to kick that group off. So we can see that we are going to form, oops, I'm running out of space over here. So we can rationalize that we are going to have something that looks like this. Okay, so that is, the first, schematic of it. And then I can keep reacting by taking another equivalent of alcohol, and I can add that directly in to my carbonyl. And you are going to get a product that looks like this. And the last step of this reaction is to just remove that final proton on that alcohol by doing this. So then your final product should be that acetal structure. So it looks like this. All right, so that's a very, very long mechanism. I'll zoom out so you guys can see that again. So basically, we took this protonated alcohol, and we made that electrophile more electrophilic. That allowed us to do nucleophilic attack with that weak oxygen nucleophile. We did a series of acid-base transfers going on over here. We did elimination of this leaving group, this good leaving group over here, and then we just added in another equivalent. So at this position, we technically had the hemiacetal, and then we continued reaction to get the acetal product exclusively, okay? And it's all fostered by the removal of water. Some points to make. So from this position on, to over here, that whole group is just a series of acid-base transfers. So you could have just drawn this product, gone right to this product, and wrote squiggly H. That is shorthand notation for a series of acid-base transfers. Perfectly legal. I highly recommend doing it on the exam because that will save you time from making, save you time and save you points because you don't want to make more mistakes. So that is, that example. So let me just erase to make more room, and we'll move on to the next example. All right, so moving down over here, we have this molecule. So something I'm just going to kind of ruin the surprise right now, something that you need to be cognizant about in this exam exclusively is the fact that we have intramolecular reactions like crazy. So we need to make sure that there is no ring closing or ring opening that I am missing on the exam. All right, so right now in its stable form, without, let's just say there is no catalyst or anything involved, this is just the molecule the way that it is. But the minute that I introduce this linear molecule into solution under acidic conditions, we will have a reaction happening. So remember, recall that the purpose of that acid is to make the electrophile more electrophilic, so it's just protonating that carbonyl group. And now, since we have this hydroxyl group, which is in the chain with the a carbonyl group, we can do nucleophilic attack within the molecule itself. So let me just number my carbons here. 1, 2, 3, 4, 5, 6. Okay, so I can draw a 6-membered ring, that looks like this. 1, 2, 3, 4, 5, 6. And I'm going to draw just the numbers in here. So 1, 2, 3, 4, 5, 6. I highly recommend drawing in numbers for ring closing so you understand where the substituents are. So at carbon number 6, we had that alcohol formation, and we also had that tert-butyl group. So 1, 2, 3. And then you would have another enantiomer of this, so it would be something like this. I could have attacked from the other face. Oops, backwards. Okay, so you would have something like that. There is no way that you could flip or rotate to make identical structures of these, so that is that. Okay, so I hope that makes sense on intramolecular ring closing. And it's the same mechanism that we saw above. Yeah. Okay, so let's talk about one of my favorite things. I alluded to it in my Exam 2 Worksheet 1 video, but these protection groups are actually really, really cool. So let's just look at the first scenario. So let's just look at this reaction scheme first. So recall from Organic 1, when we wanted to convert alcohols into alkyl halides, we could use a reagent called PBr3 to convert that hydroxyl group into a bromine. So the product of step 1 would be something like this. Okay. And what happens is the product of step 2 is just using pure magnesium and THF, so that's going to form the Grignard reagent that we talked about, you know, at the beginning of chapter 15. So we have something like this, MgBr. Make sure you have the Mg in front, guys, not the Br in front. I know a lot of people lost points on the exam for that. And step 3 would be reacting with some sort of alkyl halide. Okay, problem, and this is why I wanted to do this example. So what happens is remember, when we have these Grignard reagents, we said that that carbon that is next to that magnesium is nucleophilically negative. And then we also rationalized that the carbon that's attached to the electrophile is an electrophile. So what happens is, without even reacting with this alkyl halide, we're going to have a ring-closing reaction that forms this structure. Oops, is that 6 carbons? One more time. Yep, that one. And you are going to have a alcohol here. It's going to be like wedge and, you know, it's meso, so you don't really need to show stereochem. So actually, let me just be more accurate there. Okay, sure. Okay, so you're going to get that type of molecule, and there's nothing you can do. So now there's no reaction with that alkyl halide. That's just not going to happen. So if I were to draw that reaction, I can just do this X mark on top to indicate nothing's happening. All right, so do you rationalize how that's happening? I know you guys aren't answering me, but so what happens is that we're converting that basically alcohol functional group into a Grignard reagent. It's going to form an intramolecular reaction with the ketone. But let's say I didn't want to do that, and I had a synthesis problem where that's an unnecessary side reaction that I had. Well, I can use something called a protection group. So let's move over to this scenario over here. So it's the same thing as before, but now I have this additional step in the beginning. So this is a 1,2 diol, and this 1,2 diol is going to add into that ketone functional group to form a protection group. So let me just draw the product of that first step. So if my memory serves me right, you know, it forms this, and we didn't cover the mechanism, but it follows the same thing as before. So this is a 1, 2, 3 carbon chain, 1, 2, 3 carbon chain. Okay, and now we have this product as the result of step 1. So what that does is it makes that ketone functional group not electrophilic anymore. So now we basically kind of hid that functional group temporarily from the molecule. So what we can do now is do the same reaction that we did with PBr3. So I'm just going to erase here to save some time. So that's going to turn it into Br. And then the next step is using pure magnesium. So I can just erase that and replace it with MgBr. Now I can use that alkyl halide and do nucleophilic attack to extend the carbon chain. So it's that carbon. You know, that arrows might be not explicit, but so the product of that reaction would be 1, 2, 3. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And now we have this functional group, and that's the end of this reaction. So I can extend the carbon chain by protecting this ketone functional group with the 1,2 diol, but in this reaction scheme over here, I could not do that reaction scheme because we didn't do anything with that ketone. And then if I wanted to remove that functional group again, you know, you just add an equivalent of water under acidic conditions, and then you would get something like this, you know. So be careful with that in synthesis. 1, 2, 3, 4, 5. Yep, and that is our end product if, you know, I had a step 5. But okay, so that's just something I really wanted to point out to you. I have a suspicion that that's going to be important on this exam. All right, finally, we're on the end part of nitrogen-based nucleophiles. So let's just do a little bit of comparison between oxygen and nitrogen-based nucleophiles. So over here, I put a snippet of the periodic table. So let's just use some of our trends that we remember from Orgo 1, a long time ago. So as we go across the periodic table, we can say that we are increasing acidity. And that means that on the left side, that means we are increasing basicity over here. So that's basicity, all right? So is nitrogen or oxygen more basic based on this trend? Well, if you said nitrogen, you're right, because it's closer to the left. So nitrogen is more basic. And recall back to organic 1, we said that nucleophilicity parallels basicity. So we can say that nitrogen, since it's a stronger base, would be a stronger nucleophile than oxygen. I hope that logic makes sense. So if we had these two series of nucleophiles, we can classify this one as weak, and we can classify this one as strong. And that is going to have specific consequences with the other reagents that we're going to use. So let's just look at this ketone, and these are two different routes that we could have taken. We could have done an alcohol addition reaction, or we could have done a nitrogen nucleophile addition. So let's just pay attention to this line right here. So under I guess I would say under an alcohol addition reaction, we would have to have a very, very strong acid to catalyze this reaction to happen, and that makes sense because we need to make that weak electrophile more electrophilic in order to react with an already weak nucleophile. When we're comparing it to the strong nitrogen-based nucleophile, we don't have to catalyze this reaction with a strong acid because it's already a strong nucleophile adding into a weak electrophile, all right? So that's why we see pH of 4 to 5 versus a pH of around 2. And the purpose also is that if we had too strong of a acid, so let's just say it was like, hydrochloric acid, we would form NH3+. Immediately that acid would react with that amine, and that would form a fully protonated amine. And now, since it's fully protonated, it loses its nucleophilic properties. So, nucleophilic, whatever. Nucleophilic no more, because we don't even have those lone pairs that can do attack, okay? So that's why we have to be a little bit more careful of like the types of acid that we're using present. So it'd be sufficient just to say mild H+ on these reactions, maybe in synthesis, okay? So I just wanted to point that out. And they are both driven to completion by the removal of water. So in these reactions, you will not see, at least in these mechanisms, you will not see protonation of the carbonyl group because that's just an unnecessary reaction. So just something to be cognizant of, we have two reactions here, a primary amine and a secondary amine, and they both form two different functional groups. So let's just take the first one. So an imine synthesis. So what an imine is, it's a carbon-nitrogen double bond. So carbon-nitrogen double bond, and an enamine we'll see later is a carbon-carbon double bond with an associated amine. So we'll deal with that later. So whenever you see nitrogen-based nucleophiles adding into carbonyls, the first thing I would do is classify it. So this one is clearly a primary amine, so we are going to think that it's going to form an imine product. So I guess I'll show the mechanism over here. So we have this, generic ketone over here, and we have this amine, and we said that before that we don't need to protonate that carbonyl because of how strong this nucleophile is already. So we can just add directly into here, and we are going to get, this product. And I'm going to use my shorthand notation because I'm assuming you guys understand at this point what's going on. So we are going to form that and H2, so another H. So it's plus. So, here we're just going to do a series of acid-base transfers, by removing the hydrogen from the nitrogen, giving it to the hydroxide group and resonating down. So you can just draw immediately this product where we have a nitrogen and a hydrogen, and so this is still plus, and then our final workup step would just be to take another equivalent of, let's just say, amine in solution. I'll just do H2 over here, and we're going to show the mechanistic errors for that, just removing that, bond, and we form our amine. Okay, so that is the amine reaction. So I think that makes pretty decent sense. It's like the same generic scheme for all of these reactions, especially with alcohols. So the secondary amine addition is going to form something called an enamine. So that is going to be like this. So that is a carbon-carbon double bond with an associated amine. So I guess I'll just do this. Carbon-carbon double bond plus amine. So I'm not even going to show the mechanism for this. So you would think that we have an amine here, and it's a 5-carbon ring, so it's something like that. And now we have to decide where we want to put our double bond. So we have a redo selective choice. We can either decide to put it at this position, that didn't really help, I guess, and we can pick like another color, or that position. So remember that we want to form the most stable, most substituted alkanes. So the way that we're going to form the Zaitsev alkene, the Zaitsev product, is to put your double bond over here. All right. And that is the enamine synthesis reaction. So I think that's pretty much it to my video. Yep. So that's all the material I wanted to cover for this video. The next video is going to finish up chapter 16 material, which is going to cover keto-enol tautomerization, alpha halogenation, etc. I hope this was a good summary for you guys for your exam.